Welcome back to The Explainer. Today, we are getting into the weeds on one of the most incredible pieces of engineering in the entire human body, the ball and socket joint. We're going way beyond the basics to really understand its design, its compromises, and, yeah, its complexities. Let's dive in. Okay, just a quick heads up before we start. This is our advanced explainer, so we're kind of assuming you've got the basics down. If you're looking for a refresher or starting from scratch, you should definitely check out our foundational video on joints first. For everyone else who's ready for the deep dive, let's get to it. You know, ball and socket joints give us this absolutely unrivaled range of motion. Seriously, think about a baseball pitcher's windup or a ballet dancer's kick. But all that incredible freedom doesn't just come for free. There's always a catch. So the big question we're tackling today is, what's the trade-off?
So here's our game plan. We'll start with the technical basics to make sure we're all on the same page. Then we'll hit the core principle, that mobility-stability trade-off. We'll see it in action, comparing the shoulder to the hip, look at what happens when things go wrong, and wrap up with how we maintain and fix these amazing structures.
All right, let's kick things off. Before we can really appreciate the trade-offs, we need to get the language right. Let's build a solid technical foundation. So the fancy anatomical name is articulatio spheroidea, but really it's just what it sounds like. You've got a spherical ball at the end of one bone that fits neatly into a cup-like socket on another. It's this beautiful, simple design that unlocks all of its amazing complex movement. And that design is what makes it what we call a polyaxial joint. Poly meaning many, axial meaning axes. It can move front to back, side to side, and it can rotate. It moves on all three axes, which is exactly why it gives us the biggest range of motion of any joint type in the body. Period. Okay, so what are the actual parts that make all this incredible movement happen? Let's peel back the layers and take a look at the anatomy. Well, just like any synovial joint, it has a standard toolkit. You've got the articular capsule holding everything together, the synovial membrane that produces fluid, and the super smooth articular cartilage that prevents grinding. And then there's a special little rim of cartilage called the labrum that helps deepen the socket for a better fit. But let's zoom in on that synovial fluid for a second. This stuff is amazing. It's thick, viscous, kind of like egg whites. It's the body's ultimate lubricant, letting those bone ends glide past each other with almost zero friction. Honestly, without it, our joints would literally wear themselves down to dust. And this brings us to the main event, the central theme of this whole explainer. The one engineering principle that really dictates everything about these joints. Here it is. This is the golden rule of biomechanics. It's a constant balancing act. You can have incredible free-flowing movement, or you can have rock-solid, unshakable stability. But you can never, ever have 100% of both at the same time. This trade-off is everything.
So what tips the scales one way or the other? It really boils down to three main things. First, just the shape of the bones, how deep the socket is and how snugly the ball fits. Second, you've got the ligaments, those tough fibrous bands that act like passive seatbelts. And third, there's the active support from your muscles, like the famous rotator cuff in the shoulder, which constantly fine-tune the joint's position.
Now, let's make this less abstract. The best way to see this principle in action is to compare the two main ball and socket joints in your body, the shoulder and the hip. They're a perfect case study. It's like a tale of two philosophies. On one side, you've got the shoulder. We're calling it the agile acrobat. Its socket is really shallow. Think of a golf ball sitting on a tee. That design is all about maximizing mobility. Then you have the hip, the sturdy weightlifter. Its socket is super deep, creating this incredibly stable weight-bearing structure. It sacrifices some of that acrobatic freedom for pure raw stability. And you can see that acrobatics when you look at what the shoulder can actually do. It has an insane 8 different key movements. This is what lets you reach for something on the top shelf, scratch your back, or throw a perfect spiral. It is built for complex, 3-dimensional action. Now, the hip is no slouch, right? It still has 6 key movements, which is super impressive and lets us do everything from walking to squatting. But you'll notice it's missing those horizontal movements. That's because its deep socket and thick ligaments are saying, nope, our number one job is to keep this body stable and upright. So what happens when this delicate balance gets pushed too far? Well, those very same design choices that make the shoulder mobile and the hip stable also dictate the kinds of problems they're most likely to run into. Yeah, it's a direct consequence. For the shoulder, that shallow socket means it's the most commonly dislocated joint in the entire body. The ball can literally pop right out. On the flip side, the hip's heavy-duty job of bearing our weight day in and day out puts a ton of stress on its cartilage. That makes it way more vulnerable to the wear and tear of osteoarthritis over a lifetime. And of course, it's not just those two issues. You can get labral tears from a sudden injury or just overuse. The rotator cuff muscles can get torn, which messes with the joint stability. Then you've got weirder things like frozen shoulder, where the whole capsule just seizes up, or even more serious problems like hip dysplasia, where the socket never formed right in the first place. Now, before we talk about fixing these things, we have to do our due diligence. Quick but really important reminder, this is all for your information only. This is not medical advice. If you have any personal health concerns, please go see a qualified healthcare professional. So, given how complex and, frankly, how vulnerable these joints can be, how do we take care of them? And what can we do when they start to fail? Well, the treatment playbook usually follows a clear path, from the most conservative options to the most invasive. You almost always start with the simple stuff: rest, ice, maybe some anti-inflammatory meds. From there, physical therapy is absolutely key to fixing the underlying mechanics. If that's not enough, you might move on to things like cortisone shots, and only if all of that fails do you start talking about surgical options like a repair or a full-blown joint replacement. Okay, let's wrap this up. What are the big takeaways? Number 1, ball and socket joints are polyaxial. They're our mobility champions. 2, there's always a trade-off between how much a joint can move and how stable it is. 3, the shoulder is built for mobility. The hip is built for stability. 4, that very design difference is why they tend to break down in different ways. And 5, it takes a whole team: cartilage, fluid, ligaments, muscles, working together to make these joints function. And that leaves us with one last thing to think about. We're all living longer, and we're asking more from our bodies than ever before, whether that's in sports or just in daily life. That basic conflict between mobility and stability is still a huge challenge. So the question for the future is this: how will bioengineering, with new materials, 3D printing, regenerative medicine, how is it going to solve this paradox? Something to chew on. Thanks for watching.